This is a video for my final year project titled Time Series Anomaly Detection. To give an introduction on my project, I'll describe the problem I am trying to solve and the objective of the project. Firstly, anomaly detection in time series data can be applied to many problems and industries. Anomaly detector can be used to indicate unexpected events such as defects or system faults. Commonly, deep learning models will be used to detect anomalies due to the complexity of time series data. For my project, I will be detecting anomalies in a time series aero engine data using an autoencoder model with the aim to reduce engine downtime. The anomalies is used to detect the start of the engine degradation, which can be used as an indication of the remaining useful life of the engine for predictive maintenance purposes. After detecting the onset of engine degradation, this project takes a step further to predict the remaining useful life of the engines using deep learning methods in order to give a more accurate time to failure of each engine for better predictive maintenance and prevention of mechanical failure. Deep learning methods are commonly used in remaining useful life prediction. However, most existing methods set exact RUL labels as labels for the training data at a particular time step, but in actual fact is that different engines have different rates of degradation at each time step. Hence, cycle consistent learning is implemented, which aligns degradation data of different engines with similar degradation levels. Next, the methodology on the implementation of the models will be explained. An overview of the methodology is illustrated here. The autoencoder model will be trained on the pre-processed data, which only contains the sensor data of the aero engines before the onset of degradation. In other words, it is the data where the RUL labels is at its maximum before the RUL starts to decrease. The autoencoder will predict the onset of degradation, and a deep convolutional neural network will be implemented and trained on the data after the onset of degradation to predict the RUL of each engine. So how does the autoencoder detect the onset of degradation? The trained autoencoder model will be used to reconstruct the test data. Anomalies are detected from the reconstruction errors when the reconstruction errors exceed the threshold, which is determined by the 75th percentile of reconstruction errors. Then, the first index of the anomalies will be taken as the first point in time when the engine starts to degrade. After detecting the point in time when each engine starts to degrade, remaining useful life prediction will be done for each engine using a deep CNN model. The model is trained as follows. For each epoch, all possible unique pairs of engines are generated, and all possible pairs of sequential sensor data of each engine are passed as input to the CNN model, represented by lowercase p and q. The CNN model consists of three convolutional layers and two fully collected layers where it outputs feature representations and RAL predictions for both engines P and Q. Cycle consistent learning then aligns data from each of these engines at similar degradation levels, and this loss is calculated using a custom loss function. The mean squared error loss is computed for the RAL prediction of each engine as well. How does cycle consistent learning work? From the CNN model, we get feature representations represented by uppercase P and Q. Cycle consistent learning is implemented by computing Q hat I, which is the soft nearest neighbor of sample P I in P in the space of Q. It is computed by the product of UIK and each sample Q, K in Q. U hat IK is the softmax to the negative squared Euclidean distances, alpha ik between P, each sample P and each Qn. The cycle consistent loss function is implemented according to the following equations shown. Each sample P I in P is mapped to a soft nearest neighbor Q hat I in Q. Then Q hat I is mapped back to P. The mapping is done by computing distances beta in from Qi to all Pn and converting these distances into a probability distribution using the softmax function. In a classification problem, this distribution is compared to the true class of Pi, one hot vector Hk, using cross entropy loss. The closer Q hat I is to Pi, the lower is the loss. Then the cycle consistent loss, represented by L, is added to the mean square error loss of both engines in a pair due to RL prediction to get the total loss. Here are the results obtained from both the autoencoder and CNN model. For the autoencoder model, the predicted onset of degradation is plotted against the true onset of degradation for selected engines, are shown as example. Predicted values are lower than true values for all engines of the test data, which presents a more conservative approach where the remaining useful life prediction is implemented before the actual onset of degradation. Also, the average difference between the true and predicted values across all engines is around 13, hence the autoencoder model is indeed effective in predicting the onset of degradation. For the deep CNN model, the RUL prediction of each engine is plotted against the actual RUL for all the engines. Two of the engines plots are shown here as example. It can be seen that the RUL estimation is more accurate in later periods of the engine's useful life, as in later stages there are more fluctuations in the data and hence more significant features can be observed. Lastly, the root mean squared error is used as an evaluation metric for the RUL prediction model. The RMSE of the proposed model as compared to the baseline CNN model without cycle consistent learning is shown in the table. The root mean square error for the proposed model is lower than the root mean square error of the baseline model.